everyone. In this video, we are going to learn about equipotential surfaces and their properties. So its name implies equipotential. So potential are equal, right? So before that, what is meant by potential? That you have already learned. It is the amount of work done to bring a point charge, a positive charge, from infinity to a point where the electric field is present, or we are displacing a positive charge from infinity against the electrostatic force, and that work done is actually called what? Potential. Now here we are talking about equipotential surface. So the definition is here: any surfaces that has same electric potential at every point on it. So in order to understand this one, just discuss about one example. Let's see the picture here. In this picture, you can see here a positive charge. Just imagine a positive charge is placed in the air. What is the direction of electric field? Electric field will be radially outward, right? Now just imagine here you can see from this charge plus Q, you just take this is a point and is a point here. Just mark it as the radius is R towards this point. What is the potential at P? If I am marking here at P, what is the potential? I can mark here. Potential at P is equal to 1 by 4 pi epsilon 0 Q divided by R. Right? So potential at P here. Just imagine if you want to find the potential at this point, say it as Q. What is the potential at that point Q? Again say here the radius is once again R. That means again I can write the VQ is equal to 1 by 4 pi epsilon 0 Q divided by R. So what is the meaning here? Around this positive charge, if you take this surface means what? It's a spherical shell, right? If it is placed in air, it's a spherical shell. So at every point on that surface, potential is same. So potentially same means what? We can say that this surface, this imaginary point, you can see dotted line, this is called an equipotential surface. That means if you want to bring a charge Q from infinity to the point Q to the point P or to any point on this surface will be same work. You have to do the same work. So you can see here the potential is same at every point. So you can see here there are many equipotential surfaces are here. I hope it is clear. So any surfaces that has the same electric potential at every point. Now let's think about the properties. The first property is here. No work is done in moving a test charge over an equipotential surface. That means there is no need of any work to move a charge along the equipotential surface. Just think about an example here. Imagine this is an equipotential surface. Alright? An equipotential surface is here, marked here. And electric field is normal to this equipotential surface. That will be always normal. We will learn later. Now you can see here, this is a point A. You want to move a charge. A charge Q is here. You want to move a charge Q from A to B. Question is here, what is the work done? So as you already know, formula V is equal to W by Q. Say it as Q0. So I'm just moving another charge Q0 from A to B. So what is the work done to move this charge from A to B? So I'm writing here WAB, which is equal to Q0 into V. Here V we can write the potential difference. So what is the potential difference here? VB minus VA. We are moving from A to B. So what is the VB minus VA? VA as well as VB are equal, right? So what is the potential difference? Potential difference is equal to 0. So we can say that work done to move a charge from A to B along an equipotential surface will be 0. So this is the first property. We can say that no work is done in moving a test charge over an equipotential surface. Okay, so first property is clear. Move to the second one. Electric field is always normal to equipotential surface at every point. Alright, so just imagine, so this is a very important property, that always electric field will be normal. Electric field will be normal. So just imagine this is an equipotential surface. Equipotential surface. So definitely electric field will be always normal, right? But you just imagine this is not normal. Just imagine this is the electric field which is not normal to the surface. So what will happen here? There will be a component along the surface. A component. For this electric field, there will be a component along the surface. Clear? That means if you want to move a charge along this surface, you should do a work against this electric field. Right? That means you should do a work to move a charge along the surface. So what we have already learned in the first property, here there is no need of any work done, right? So here in this case that is wrong. So electric field will be always normal to the surface. Now look at the third property. Equipotential surfaces are closer together in the region of stronger field and farther apart in the region of weaker field. What is the meaning? If the electric field is more in a region where the equipotential surfaces are very closer, in a region if the electric field is much weaker, what will happen? The spacing between the equipotential surfaces will be more. So in order to see or to understand this one, we should know the formula. The relation between electric field and electric potential. Electric field is the negative of potential gradient. That is E is equal to minus dV by dr. Here dV by dr is called what? Potential gradient. That means if, just imagine dV is equal to constant, the same change in potential. Same change in potential, if dV is constant, you can write here E is inversely proportional to dr. So dr is directly proportional to 1 by E. Now let's see this picture. This picture actually represents a dipole. So as you already know, electric field lines starting from positive and ending at negative. Thick line represents here flex line or lines of force, electric field lines, and here dotted line represent the equipotential surface. You can see here there are many equipotential surfaces are shown here. Where is the equipotential surfaces are much closer? Definitely we can say that in between negative and positive charge. That means electric field will be much strong in between negative and positive. If you go outside of this negative and positive, or very just moving away from negative and positive, you can see here the spacing is increasing. Spacing is increasing. What is meant by spacing is increasing? Mean the electric field is much weaker. So this is the third property. Okay, move to the next one, the fourth property. No two equipotential surfaces can intersect each other. So you have all learned the properties of field lines. What will happen if these equipotential surfaces are intersecting each other? If they are intersecting each other, at that intersecting point there will be two different values of potential. So that is not possible for an equipotential surfaces. Okay. Now, so these are the four properties of equipotential surfaces. Now just think about various examples for equipotential surfaces. So, a few examples we will discuss here. The first one we will be discussing here, that is a positive point charge. Imagine a positive point charge is placed in air. So we have all learned just now what is the equipotential surface shape. If it is placed in air, if a charge is placed in air, the equipotential surface will be what? A spherical shape, or we can say the spherical shell. So look at the picture here. A positive point charge is placed here. The green line here represents the flex lines, where the dotted line represents what? Equipotential surfaces. So what is the shape of the equipotential surface in this case? It will be in spherical shape. If it is in air, it will be in spherical shape. So this is the first example for an equipotential surface. Look at the second one. Two equal and opposite point charges. I've also shown that one before. So you can see here this same picture here. A positive and negative charges. That is an example of a dipole also, if it is equal and opposite. So you can see here at this picture. Look at the picture here. Is this spacing is same here and here at the point 1 and at the point 2? No. That means the electric field will be more. Electric field will be more in between the positive and the negative charge. Here you can see here the spacing is more. Spacing is more. So what is the meaning? Here the electric field is minimum or less. We can say that, not minimum, less. Okay. So this is another example of equipotential surface. Okay. Now let's move to the third one. That is the two equal positive point charges. As you already learned that one. If there are two charges are equal, there will be repulsive force will be there. And you have already learned that in between two equal charges, there is a point is called neutral point, where there is no force of attraction or repulsion is there. So maybe you can say here, exactly at the center, there is no electric field lines exactly at the midpoint. But the potential here will be constant. Potential will be constant. So here also once again say here, where is the equipotential surfaces are much closer, left side of these two charges, positive charge and here also positive charge. So here these points where we can say that electric field strength will be more than in between two positive charges. Okay, so this is another example. So you can see here the shape of the dotted line or the equipotential surfaces. You can see here many other. This is the one diagram also you can see in your NCERT textbook. You can see here two positive charges. There is no field lines are on here, but there is only equipotential surfaces are shown. So once again you can say here the equipotential surfaces are here farther apart, or the distance is more, right, in between two equipotential surface. So here the electric field will be less, and here in this side electric field will be more. Okay. Now look at the fourth case, that is a uniform electric field. So you already know what is uniform electric field in this case. So this is an example of uniform electric field. Okay, the lines of forces are shown here. If you take any point here, if you take any point or any surface, maybe a plane surface here, first surface, at any point if you take, this is a point P and this is a point Q, this is a point R, at all these points the potential will be same. That means the amount of work to bring a charge from infinity to these points are equal. So same way, in along this electric field line there are many equipotential surfaces are there. So these are the example for equipotential surfaces. Hope you understand this one. Thank you.